Hi everyone. Let's discover a few properties of definite integrals. In the exercise below, we're given three definite integrals. We must evaluate them by interpreting them as area, and then see if we notice anything special about our answers. If you would like to try this exercise on your own, stop the video now. You can also download these notes using the link in the video description. Let me start by evaluating the definite integral in part B. This is the signed area of the region between the graph of the function f of x equal to x and the x-axis between x equal to 0 and x equal to 2. We can see that region below. That region is a triangle of base 2 and height 2. Area of a triangle is computed by base times height times 1/2. In this case, I get 2 times 2 times 1/2, which gives me 2. This definite integral equals 2. In part C, a similar situation happens. This time, instead of a triangle, I have a rectangle. This rectangle has base 2, height 3. The area of this region is 6. The definite integral of 3 between x equal to 0 and x equal to 2 evaluates to 6. In the first picture, I see that I can split my region into two regions, a rectangle and a triangle. The area of the rectangle is 6. The area of the triangle is 2. The area of this region is 8. The definite integral of the function x plus 3 between x equal to 0 and x equal to 2 equals 8. You probably noticed that the value here equals the value here plus the value here. Said differently, the integral from 0 to 2 of x plus 3 dx equals the integral from 0 to 2 of x dx plus the integral from 0 to 2 of 3 dx. What simply this means is that whenever you have an integral of two functions added to each other, you can split that definite integral into two separate definite integrals, one of the first function and the other one of the second function. This holds for any integrable functions f of x and g of x when added. Let's discover another property by evaluating two more definite integrals. If you would like to try this exercise on your own, stop the video now. The first definite integral is the definite integral of 3x between 0 and 2. In the picture below, you see the graph of the function 3x, and you also see the region under the graph of that function. The area of this region is 2 times 6 times 1/2, which gives us 6. This definite integral evaluates to 6. The second definite integral evaluates to 2 times 2 times 1/2, which gives us 2. The definite integral of x between x equal to 0 and x equal to 2 is 2. What's the relationship between these two definite integrals? One is 3 times bigger than the other. This makes sense. There is a 3 right in front of x, making the value of this definite integral 3 times bigger. Which means if we increase or multiply this by 3, we get the same answer. Said differently, when you have the integral from 0 to 2 of 3x dx, this is not exactly the same as the integral from 0 to 2 of x dx. But if you multiply this second integral by 3, you will get the same answer. You will also get 6. You can understand this property as if you have a function multiplied by a constant, you can take that constant, in our case 3, and move it outside of the integral and obtain the constant times the definite integral of the function without the constant. The two properties we just discovered are listed in this table below. When you have two functions added in the integrand, you can split the definite integral into two. And whenever you have a function multiplied by a constant in the integrand, you can take that constant outside of the integral. Let's discover a few more properties. In this exercise, we're given again 3 definite integrals. We must evaluate them and see what we notice. If you would like to try this on your own, stop the video now. Note that here the function does not change. The function is always x. What changes are the limits of integration from 0 to 2, from 0 to 1, and from 1 to 2. Similarly, the regions change. The region goes from 0 to 2, the region goes from 0 to 1, and the region goes from 1 to 2. Without even looking at the answers, I can tell that if I take this region and I add it to this region, I will obtain this region. We can verify this. The area here is 2 times 2 times 1/2, which is 2. The first definite integral gives us the value of 2. The area of this region is also a triangle. 1 times 1 times 1/2 gives us 1/2. The second definite integral is 1/2. The last region I can compute by splitting this figure into 2 familiar geometrical figures, a triangle and a rectangle. The area of the triangle is 1/2. The area of the rectangle is 1 times 1, that's 1. Altogether, this entire area is 1.5. Note that if I add these two numbers, I get this number. What we just discovered is that if I take the integral from 0 to 2 of x dx, I can instead compute the integral from 0 to 1 of x dx and add to it the integral from 1 to 2 of x dx. This property will hold for any integrable function, not only just x. In the next exercise, we see that we have a definite integral of the function x between 1 and 1. We can guess that this definite integral evaluates to 0, and that is because there is no area under a singleton point. Which means that most likely any definite integral from one number to itself of any function is always 0. In fact, mathematicians proved it, and this is always the case. Let us discover one final property. Again, we're given 2 definite integrals. We must evaluate them and see what we notice about our answers. In the first case, we're given a definite integral from 0 to 2 of the function x. We see the region under the graph of the function f of x equal to x in the picture below. This definite integral gives us the area of that region. This is a triangle with base 2 and height 2. The area of this triangle is 2 times 2 times 1/2, which gives us 2. Remember, when we defined definite integrals, we used approximating rectangles. Implicitly, those rectangles went from 0 to 2. The width of each approximating rectangle was denoted by delta x, and we computed the width of each approximating rectangle by taking the upper limit of integration, subtracting from it the lower limit of integration that gave us the length of the entire interval, and dividing that by the number of approximating rectangles. In particular, that number was a positive number. 2 is positive, n is positive, 2 divided by n is positive. If we apply the same logic to compute delta x for the definite integral on the right side, we will get the upper limit of integration minus the lower limit of integration divided by the number of rectangles, giving us a negative number. Note that the only difference between this number and this number is a minus sign. The height of those approximating rectangles, regardless if we draw it from the left or from the right, are the same. Which means that the only things that changes is delta x. Delta x in the first case is positive, delta x in the second case is negative. Which means this answer will be exactly same as this answer, but will have a negative sign in front of it, and we will get -2. This means that if you want to compute this integral, you cannot simply compute this integral. If you want to compute the integral from 2 to 0 of x dx, you will not get the integral from 0 to 2 x dx, because your answer will differ by a minus. If I add a minus in front, then these two answers will be the same. If I put a minus in front of this integral, then these two answers will be the same. What we just discovered were these three properties of definite integrals. The definite integral from a number to itself is always 0. If you have a definite integral where the lower limit of integration is b and the upper limit of integration is a, and you ever want to flip the order of those limits, you must put a minus sign in front. And finally, if you have an integral, definite integral from a to c, you can split it into an integral from a to b and integral from b to c, where a, b, and c can be in fact any numbers you wish.